are you?
Hello, everyone.
Ready?
Let me, didn't know how to turn
lost
my
your
video
screen.
on without stopping the broadcast, but I think I
Sure.
can get back pretty easily. Okay, I'll start when I'm cleared.
Okay, great. So, yeah, welcome everyone to the last set of talks and discussions. So we're very happy to have Matthew Baumgart talking on de Sitter diagrammer, and yeah, take it away, Matthew.
Okay, well, thank you so much to Guy, Enrico, and everyone else involved for putting together this wonderful workshop, and it's really a deep honor to get to give a live talk here. I'm going to be talking about some work that came out the end of last year with Raman Sundram. It was recently published, and we have a technical follow-up, which you'll explain the context for shortly, hopefully coming out later this month. And also hopefully by the end of this talk, this funny version of a Feynman diagram will become meaningful to everyone. So just to give a bit of intro, this is a cosmology workshop. I don't think I need to motivate de Sitter too much, but just to justify my own presence here, for anyone who knows me and other things I work on, I'm really a particle phenomenologist. This is by far the most formal work I've done. So just a sociological question is, why am I writing these papers? And the answer, as we all well know, is that de Sitter is not just any old space-time. Nature seems to have a deep affinity for it, both in our cosmological past with inflation, the coming cosmological acceleration era, are both very approximately de Sitter-like. And of course, if we want to solve the phenomenological problem of the cosmological constant value, something like eternal inflation suggests itself as a solution. So I did feel the need to put one I did feel the need to put one piece of data in my talk, which is the tilt of the scalar spectrum. We see it's not quite 1 over k cubed, and the fact that in a pure de Sitter it would be exactly 1 over k cubed is going to be deeply important for what we're looking at. Just to drill down a little bit on motivation, 20 plus years after the discovery of dark energy, it would be great if we could reduce calculations for the landscape to the technical, rigorous level that many of the calculations in this talk have described. What I would describe what we're up to with trying to understand very light scalar fields on a fixed de Sitter background is it's a warm-up to a toy landscape. Now it's a warm-up because we don't allow back reaction, but our final result is the probability distribution over scalar field strengths at very late times. And if you could just turn out a bit of back reaction, you would be sampling a real landscape, a probability of getting different CCs throughout the universe. So we are getting toward having very controlled, strict calculations probing the idea of a landscape. But of course, as we know, that's not all. In particular, these sort of infrared subtleties and issues in de Sitter, I think, are a little bit analogous to what renormalization was in the 40s and 50s. It's not so much that it's the phenomenology we're worried about for, say, cosmological inflation. It's more we're just trying to push on the whole formalism and understand it conceptually, and that could have implications for the holography of de Sitter. That could have implications for understanding what happens when dynamical gravity is included in de Sitter. There are some similar infrared issues that go there. But before we get to any of that fun stuff, we should just absolutely be able to skewer and nail a single light scalar field where we don't even allow it to back react and change the space-time. Okay. So here's my theory. It's just a scalar theory, and we're going to go ahead and treat it as strictly massless. Although again, one could always include a tiny mass and deal with those corrections. So v of phi is almost always going to be phi to the 4th, although conceptually other polynomial potentials, at least for single minimum theories, are included in everything I'm going to say as well. I'm going to make the standard choice that the scalar is in the bunch Davies vacuum, since that's the uniquely de Sitter invariant, and Minkowski-like in the UV choice, although there is an interesting side topic on whether other de Sitter invariant vacuum could be made at all consistent.
So sorry, why do you need de Sitter invariance? I mean, we heard in Leonardo's talk, for example, that we understand even better now that inflation is robust against very wild variations of the field early on.
So yeah, as we'll come to see, we will ultimately show self-consistently that the details of the initial state, again, as you put it, are robust to the conclusions we're going to draw. But just to pick a starting point, we're going to begin with quantitative AVs, and the de Sitter invariance actually we're going to violate off the bat in order to regulate the theory in the infrared. So if you want, this is an ansatz that we'll plug in, and then we'll come to see just how robust this is against deviations from that. So if I do make that choice, then this is the 2-point function I get, and we see in the denominator there's the famous 1/k cubed that Planck almost sees in the sky, and this function is quite innocent looking in momentum space, but if I just ask for its Fourier transform, I'm stuck with an infrared divergence in the IR. This is a dk/k integral. Anything about the UV, we're going to invoke the fact that in the deep UV of the theory, things should go over to looking Minkowski-like, and everything we know about ultraviolet regulating and renormalizing ultraviolet divergences is going to pass through. So the more important thing is this infrared divergence, which we can't just remove by local counter terms. One technical issue one wants to decide up front is whether to call that a co-moving or a physical IR, a physical momentum cutoff. If you imagine that this infrared regulation is coming from the fact that you started in some non-de Sitter theory that had a manifestly safe infrared, you see that would cut off the infrared momentum. And so at a technical level, that's what we're going to put in. Of course, ultimately, we're going to be able to remove this regulator. So if you can take it to zero, one could presumably take multiple routes to that conclusion. But I think since this picture is most physical, it's also technically the simplest. Okay, so I regulate with an infrared co-moving cutoff, and I can now write down a non-infinite, non-pathological position space result. Here it is, but you see, of course, that it is sensitive to this cutoff, and it appears to logarithmically diverge as that cutoff goes to zero. Cutting off the momenta in this way also brings in an early time cutoff, and the details of that exact relation, whatever order 1 or order some power of pi factor sits there is not particularly important, but just know that the initial time, our initial time cutoff is going to scale like the inverse of this co-moving infrared cutoff. So now we have a task, which is sitting in every propagator. We have this sensitivity to, now we can rephrase it as a sensitivity to the initial start time of our scalar theory. And this appears to be problematic because in principle, I can let this theory run for an arbitrary amount of time. And so no matter how perturbative I dial my coupling, I seem to have this proliferation of sensitivity to the initial time. So eventually, you hand me a coupling, fix it maybe up to some amount of standard running, and yet I can wait long enough and overwhelm that coupling by these time-dependent factors. So we're going to attack this problem in 2 steps. We're first just going to diagnose how bad is this sensitivity to the initial time or to our infrared cutoff. And then having diagnosed it, we can attempt to regain control of the theory. And just to give away the punchline, we're going to regain control by landing on Starobinsky's stochastic inflation, but we will come to understand it as a strict approximation to the underlying quantum field theory, as opposed to what I would say on his part was a highly motivated ansatz. Okay. So to diagnose this problem, we need to think about what is our sort of our quasi-observable we have in mind that this problem could infect. And we're going to be taking a standard in correlation function calculation, and for simplicity, we're going to take the operator that we're taking expectation value of to be at a single space-time point. It is not terribly difficult to move those phi's around to be at different spatial points. It gets a little more technical if you start moving them to different times, although Leonardo and Victor have done some work on extending that. But just as the simplest possible starting point, we're just going to take this as some local operator, which you can think of as phi to the n in our perturbative theory. And then, and so what we see in this purple equation is this is sort of the standard, no one disagrees with formulation of an in calculation. You see I've sandwiched it explicitly between this state I'm calling BD prime. The prime is just denoting the fact that I've cut off the infrared with this regulator. Otherwise, it's the bunch degrees vacuum. Now, what's very useful to us, both technically and conceptually, is this reformulation of in perturbation theory that comes from Weinberg, where if you just start tracking, where these H-ints appear from the Ket evolution and the Bra evolution, they actually package themselves into this complete set of nested commutators. Okay? So that's a very beautiful reorganization. One particularly nice thing about it that we're going to make heavy use of is the fact that it exhibits manifest causality. There's just one problem with this reorganization. It actually holds at the operator level. I could take those external states off and just come to understand it as the reorganization of those exponentials sitting on the other side of the operator. But of course, in a real calculation, if we want to do perturbation theory, we need to project the true interacting ground state onto the free, in this case, Bunch-Davies vacuum. And the standard way we do this, like we learned in our first quantum field theory class, is to do these I epsilon deformations to the, one way to phrase it is an I epsilon deformation to the time contour. But now you see there's a problem here because we've done a different deformation to the Ket evolution operator and the Bra evolution operator. And so I can no longer blithely interchange, I can't put the H-ints on the same footing as I seem to in this commutator equation. And so this is the context for this technical follow-up that Raman and I hopefully will have out soon. But the basic way it works is it follows on this conjecture from Kaya a couple years ago that basically says that while in the standard I epsilon deformation, it would appear problematic to use Weinberg's equation, there is in fact a manifestly unitary I epsilon deformation that gives exactly the same correlation functions in the end. I mean, this epsilon is doing something very crude. It's basically just letting you remove what would otherwise be an ambiguous integral evaluation from having a pure phase in your propagators. It lets you remove it. In fact, in practice, it lets you throw it out because you wind up taking some e to the epsilon times minus infinity. And so what we can show is that if we take the standard in I epsilon prescription in the diagram, we always find there's a net epsilon suppression. And if there's always a net epsilon suppression, then we could move to an alternate prescription where you put an epsilon suppression on every single propagator. And then whether you have epsilon or n epsilon, of course, that's irrelevant. You just care about the net suppression. And what this diagram is meant to show, what these red terms are, if you track where the epsilon dependence is in any line, as you evaluate all of your vertex integrals, you in the end are always assigning the time in a vertex to either the earliest vertex time, if you think about each contribution being time ordered, or you're evaluating it at the ultimate correlation time. And you see that no matter how you route it, you always get a net suppression. So if you try to trace through, say, on those leftmost lines, you see that if you try to assign one of those vertices to ultimately take the integration value a to v, well, then the propagator connecting that vertex to external correlation time gives you an e to the epsilon a to v minus eta, which again gives you a net cancellation. So those are just the details of that. Hopefully we can have something out in a couple of weeks.
Matthew,
Okay. So that's really just an aside.
Matthew, can I ask a quick question? So now you have an earliest time from which your integrals begin. So do you still have to go infinitely long along the Euclidean time direction to project onto the interacting vacuum?
That's right.
Okay.
So yeah, I set up so I can take any I can take any contribution in perturbation theory, say fix the order of perturbation theory, and then let me just I can chop up all of those contributions into a set of strictly time-ordered vertices, and then I'll define my integration limits so that there's only one integration variable, which will be the earliest time, what I'm calling a to v in this diagram. There's only one earliest time that actually goes all the way to minus infinity and needs some sort of epsilon, just at a formal level, needs some sort of epsilon factor in order to define the integral. So as I do each of these integrals, each of these vertex integrals, basically the times keep getting evaluated earlier and earlier and earlier. And I can imagine this case where I've done every single integral in the graph except for a to v. And then I could just look, did I get a net suppression with an e to the epsilon a to v, or did I somehow cancel everything and then I would just have a net 1, and then that would be problematic because the epsilon wouldn't be doing its job to render these integrals well defined.
Okay, thanks.
So, did you have a further question, or should I proceed?
No, please go ahead. Thank you.
Okay. Okay. So taking this Weinberg nested commutator formulation of in perturbation theory, the reason that winds up being useful for us is it lets you use a manifestly causal basis of propagators. And just like in standard NN, there are 4 propagator types one can consider. But we can actually reduce that to, in practice, thinking of two types. So there are retarded propagators. There's propagators that go like formal commutators, and since the vertices of those nested commutator correlation functions are time ordered, these are just retarded propagators. I can put a theta function in front of each of them, and then I have anti-commutator type propagators, which I call G+. And if I just do the soft momentum power counting, since it's the IR that I'm worried about for this problem, I notice that there's a very strict hierarchy. In particular, the retarded propagators scale like k to the 0. The anti-commutator propagators scale like 1 over k cubed. I mentioned that there are 2 other propagator types. Those are just simple Whiteman functions, which I can think of as combinations of GR and G+, and so their scaling in the IR is also goes like 1 over k cubed. Yeah. So if you were just, if you just didn't think about the causal structure at all, you would say, oh, if I want the most infrared sensitive contribution I can possibly get, I'll take propagators everywhere. Those have the most support in the IR. But that nested commutator formula shows you that, well, if you tried to do that, you would actually get 0 because of this commutator structure. You need to have at least 1 commutator per vertex in your diagram. You need to have at least 1 commutator involving the operator you're taking the expectation value of. So that tells you, so you can't get away with no retarded propagators, but it tells you that you want to economize over them. And so just to establish a graphical notation, we're going to take the retarded propagators seen in this right-hand figure. The retarded propagators will be solid lines, and these anti-commutator propagators we're going to take to be dashed lines. And so what I have here is an example of 2 two legal non-vanishing graphs. You see that they each have a retarded propagator touching each vertex, and they touch the external correlation point. Now, in the top diagram, they touch the touch the point in two places. In the bottom one, they touch it in only one place, but those are both fine. We'll come to understand what the difference between those graphs. So, just to belabor this for a moment, if I imagine having a particular graphical contribution, here I'm showing flight cube theory just for visual simplicity. So in the top graph here is just meant to be the kind of topological skeleton of the diagram. This middle graph labeled LL, that's our leading log contribution. It has the fewest number of retarded propagators that will give a non-vanishing contribution. That NLL graph contributes, but you see we've taken a retarded propagator where we didn't need to. And so that basically we gave up a chance to get a 1 over k cubed and got a k to the 0 instead. That's less support in the IR, and we can show that there's no way to make up that difference. And I'll just put in a little plug that in 2006 there was an UT Austin postdoc, Mousseau, who formalized Weinberg's nested commutator formalism in this graphical way, where your basis is G retarded, G plus, and the two different Whiteman functions, as opposed to the usual set of 4 in propagators, which are not manifestly causal. So what's interesting is that if we look into the graph theory of this of these rules to give you a non-zero leading log contribution, you see the very interesting fact that every leading log contribution takes the form of the retarded propagators forming tree subdiagrams in whatever diagram I've put down in front of you. So these diagrams on the right are some high loop order diagram, and yet the leading log non-zero contributions, if I trace the retarded propagators by solid lines, I see that they form trees. So the top graph, there's just a single tree. The bottom graph has a pair of trees, but they're always trees, and the trees always touch one and only one external correlation point. And so when we found this fact, this made this statement that the superhorizon modes of de Sitter are semiclassical. This finally made it sharp and graphical to us. There's many different notions of semiclassicality in Feynman diagrams. Sometimes we see tree level as semiclassical, or maybe like the ladder exchange between two objects in a bound state is semiclassical. Here is a slightly different notion of semiclassical. What it's telling us is that something about this dynamics is evolving classically, and yet it's convolved with all this quantum noise, which we'll come to see in a moment. Okay. But just to finish diagnosing our infrared divergence, if I take the contribution to a correlation function, what does that look like at a conceptual? Can I write down a sort of schematic equation? And it's the following. I only have as many retarded propagators as I need, which is to say, if my graph has V vertices, I have V of them highlighted in brown, VG retarded propagators, and then the rest of the propagators are going to be these anti-commutator propagators, and there are P minus V of those. Again, anything that the strict Mousseau graphical formalism would have called a Whiteman propagator, we decompose into G plus and GR, and we just keep the G plus piece since we're tracking the infrared sensitivity. And then if you were to just look, where is the sensitivity to the infrared cutoff in this integral? You see it's sitting in all of the lower integration limits. So in the momentum integrals, it's sitting as the co-moving IR cutoff, and then in the time integrals, it's sitting as the early time cutoff. And then, so I've put in that these propagators are already expanded in the infrared limit. I can make one further technical simplification, which is to say that this infrared this leading infrared retarded propagator shown in these blue equations. It goes like k to the 0, as we can see. Strictly, it's eta cubed minus eta prime cubed, but it's straightforward to see that that's dominated by one of these times being parametrically larger than the other, so we can drop the later time. So we're just left with a propagator that goes like eta cubed. And so what you see is that each of these integrals is going to give us a log KIR. Either we're doing a d3k over k cubed integral from the g plus propagators, that's a log, or I'm doing an eta cubed over eta to the 4th integral from the vertex integrals, that's a log. So the net diagnosis is that I have a power, if I switch back to coordinate time, I have t to the p, where p is the number of propagators in the diagram. So here's a set of graphs where that scaling would be t to the 5th. And so again, no matter how tiny I set my coupling, the ultimate contribution of the correlation function will overwhelm it. So that's the problem. Of course, we now want to cure it and be able to do computations. So to make progress on that front, we're going to go back to this structure that the retarded propagators form trees sitting inside any Feynman diagram contributing to this fully quantum field theoretic correlation function. So let's begin that route by looking at what perturbation theory is in a classical field theory. So if I'm just doing classical field theory for the moment, and I want to know, I want to solve some perhaps very non-trivial field equation, there's a graphical formalism for that, certainly not as familiar as standard QFT Feynman diagrams. Working in phi cube theory again for some, here I've drawn an example of order correction to a classical field theory solution. So all of the solid lines are again retarded propagators, just like our QFT diagrams. And what I've done is for each of these retarded propagators, it ultimately ends in an insertion of the free theory field solution, whatever I could solve exactly. Okay, and I've suggestively drawn it as a dashed line going to a sort of source. And if you were doing classical perturbation, if you're really caring about the classical field theory problem, what you would of course do is by invoking some initial and boundary conditions, you would plug in each of these phi naughts as some classical function, and then this graph is really, it's just a shorthand for a bunch of convolutions, and it would give you your higher order perturbative correction. Right, because that's what classical field theory is. It's trees of retarded propagators, each of which is ultimately capped by the free field solution. So this is what we see in this blue equation. I'm showing it at first order. I have on the left-hand side, I have my for the de Sitter equation, I have my free theory differential equation. On the right-hand side, I have my interactions. But if I can solve the theory perturbatively, I can put in the lower order solutions on the right-hand side as inhomogeneous terms in the equation for the higher order pieces. But I know how to invert the left-hand side. I invert it with the retarded Green's function, and of course I could work out this formalism to any order. But what I see from this in my quantum field theory is that what I can think of myself as doing, and in a quantum theory graph, is each of these trees of retarded propagators is giving me a classical perturbative correction to the field. But instead of doing what I would do in classical field theory and coming along and giving you an actual function for phi naught, I'm sampling over my phi naughts from the free theory quantum distribution. They're all entering in as these anti-commutator two-point correlation functions. So I could just take, these are the same two diagrams I used to introduce the graphical notation. I could just imagine taking them and snipping all of the dashed lines, and for the moment thinking of those snip lines as insertions of the free field for a classical perturbative calculation. But then what the diagrammatics is telling me to do is sew up all of those dangling phi naughts in all possible ways, and then evaluate them with the anti-commutator two-point function. One further simplification for this, for the light scalar in de Sitter, is that we not only do we get to do the semi-classical evolution, but the equation of motion is approximately first order. If I look at what this soft retarded Green's function is the Green's function for in terms of a classical field theory, it's the Green's function for the phi dot equals 0 equation in de Sitter space. So it's both semi-classical and first order, which makes the problem very tractable. So this purple equation is what each of these phi's that's sitting at the end of one of these retarded trees is the equation it's solving. So if I were to ignore that highlighted phi dot term at the moment, that would just be phi dot proportional to v prime. So I see if I turn the interaction off completely, I get phi dot equals 0. Now, I've included this phi naught dot because I know that ultimately, even at the free theory level, there is a non-trivial time dependence in my quantum fluctuation. So I can think about this as a some source inhomogeneity that even affects the free theory. But the nice thing about this source is that if I evaluate phi as a function of phi naught, it is the same whether I turn on this source or not. So of course, the phi naught that I plug in is different. It's different from what it would be in the true classical the true classical field theory. But as a formal function of phi naught, it's the same free theory function. So again, what I'm doing when I'm computing any QFT correlation function is I can think about doing, if I think about, I'm going to Wick's theorem everything down to two-point functions like I usually do in perturbative field theory. So I can think about doing all the contractions that give me retarded propagators first. So at that intermediate step, my correlation function looks like this expectation value of all these different classical field theory perturbative diagrams, and I can organize them by perturbative order, right? So here I've shown the first three orders. And now I can go ahead and take my remaining G plus two-point functions, which means I sew up all of the dangling ends on these classical perturbative diagrams, but I know exactly what that G plus functional dependence is. So to make progress, to restore computability to the theory, let me take what I've learned and ask about the time evolution of my expectation value. So I imagine taking some generic phi to the n expectation value. I'll take its time derivative. I see that that's going to give me the expectation value of phi dot, and I'm just going to plug in. I know that my diagrams are solving a particular equation for phi dot, so I plug it on the right-hand side. I have this first term on the right-hand side is my v prime piece, the piece that's coming from the pure classical evolution, and then the second piece is corresponding to quantum noise. Now, the nice thing about the quantum noise term, as we see in these colored equations at the bottom, is that the only way that quantum noise term can contribute when being differentiated with respect to the final correlation time, right? Because the soft propagator doesn't depend on the later time in a controlled approximate way, the only way it gives a leading contribution is if that fluctuation connects to another fluctuation also at the correlation time, which is to say it's a coincident retarded propagator, and that gives me just a corresponding power of Hubble.
Sorry, can I ask a question? Brief question. Maybe you're still getting to this. You said you're going to connect to Starobinsky. There he makes some separation into long and short modes, and the short modes contribute the noise. Is that separation in here anywhere yet?
I mean, it's in here in the sense that I'm taking everything in the soft limit. So I don't. It isn't like I'm. I'm not doing what I think Starobinsky did, what a lot of literature does, where you sort of, you're formally keeping around some, you know, phi less than, phi greater than. I'm really just taking the full field theory and just expanding everything in the soft limit, and then also in this strongly ordered time limit, and then just seeing what does that give me. And what I see is that what's sort of the piece that's kind of not quite coming from the deep infrared is precisely this, you know, these, on this slide, these red equation terms, that if that's sort of having a fluctuation, a sort of Hubble scale fluctuation, basically right in the last time step. So these terms are going to become Starobinsky's drift and diffusion terms. Right, so what makes this, and you know, I think this is an important point. What makes this a little bit different from kind of standard, you know, mindless effective field theory, you know, let me just, you know, just integrate out everything above some scale and just keep my eyes set on the lowest possible scales I need to keep track of. It's this noise. But I'm still getting this noise by just taking my Green's functions, expanding them in the soft limit, and seeing that I do, if I'm careful and I acknowledge the fact that I could have a contribution which is just 2 phi naughts that connected by a free propagator at the correlation time. I see that is not a contribution I get to drop, unlike the contributions I would get from this phi naught dot if I consider this retarded propagator propagating into the diagram. This left blob would be a contribution where that phi naught dot is contracting via an interaction to the rest of the diagram. That I see from this, just taking the soft expansion picture, is subleading. But this right case isn't. So, what I am not doing is separately keeping track of hard modes and soft modes at any kind of operational level. Okay, so in a way, this is the closer cousin of this is probably not sort of effective field theory, but more this technique of method of regions, where you realize that your amplitude or your correlation function contributions are dominated by certain sectors of momentum space. And so you just go ahead and, you know, after you've got the diagrams, you come in and say, well, I can't do the full integral, but I know the pieces I need to keep, so I'm just going to expand and get an answer that way.
Okay, so I mean, in the end, that means it is shorter than absolute zero modes, of course, that contribute noise, that fluctuate, and that's what you're seeing here, if I understand.
Right.
Yeah.
Right.
Okay.
Right.
Okay. Thanks a lot.
Okay. So now that I have this update equation, so this blue equation is just, I've now plugged in for the dominant contribution to phi naught, which is just that free propagator at correlation time, and this takes this, you know, this very nice simple form, and I can actually solve. In fact, you know, starting from Starobinsky, Thomas and Woodard in the mid 2000s got to this equation, and you can solve it in an iterative way, and we can check that our power counting is self-consistent. I was saying that I would get a t to the p for an arbitrary graph with p propagators, and if one drills down in this equation, it converts it to diagrams. You see that's in fact what you're seeing, that you're getting contributions at every order, at every possible t to the p. Just as in a personal aside, this bottom term, this 35n cubed, blah blah blah. Back in grad school, Nima told me, "Why don't you see what's going on with this?" And Cliff Chung and I spent a couple weeks deriving that very painfully as a 2-loop calculation. And when you see something like that work out, you know, including the 74, I thought, well, something about Starobinsky isn't crazy. And so that's what led me into what became a sort of 10-year journey through the topic. Anyway, if I have this update equation, if I have it for an arbitrary endpoint function, I can, of course, I know the answer from Starobinsky, but maybe if I didn't know him, we could make a particularly educated ansatz that if you have it for an arbitrary endpoint function, maybe you can get the evolution equation of a generating function where, you know, I compute the, I would compute an expectation value via this kind of cyan highlighted equation. And this update equation for the generating function is in fact nothing other than Starobinsky's famous Fokker-Planck equation, where I see the left term on the right-hand side is the drift term. This is the interactions, which as we've seen are coming from the classical piece of the theory. This is everything giving us these nice trees, and then there's the quantum noise coming from this diffusion term. Okay. There's a whole mathematical physics literature on the Fokker-Planck equation. Of course, its solutions are difficult in general, but what we see is that their structure has the following form, where there's an e to the minus v piece, and then there's these pieces that look like some function times e to the minus gamma nt. One way you can think about solving this is you can do a couple changes of variables and make it look like a Euclidean version of the Schrödinger equation. These gamma n's are strictly positive, and so as one goes to very late times, basically, independent of the details you put into the initial state, everything is just attracted to an e to the minus v solution. In particular, you see that any dependence on that infrared cutoff is now gone. Okay. So we have a non-perturbative solution now to the theory, even though perturbation theory was breaking down on us horribly. If we ask some basic question like, well, what does, say, the two-point function look like in the infinite time limit if I just solve that equation? I see it has this very non-perturbative form of something going like the inverse square root coupling. If you ask yourself, physically, what does that mean? Well, it's telling you that the energy density in the scalar field is going like Hubble to the fourth, right? Which is exactly what you would have guessed if you didn't know anything else about the problem. And so, what this Fokker-Planck equation is telling you is that the free theory is wanting to random walk off to infinity. If I remove the interaction, it would just be a diffusion equation. So it would walk as far as it could. Of course, in a free theory, there's nothing wrong with taking field strength to be arbitrarily large. Once I put in the interactions, of course, I have a classical potential trying to roll this field back down to the origin. So these two forces are in competition with one another, and they kind of fight each other to a draw. The fact that the solution is coming out as Hubble to the fourth, I would say, is suggestive that if we could go to higher orders, we would find that what we might call next leading log, the things that are subleading before resummation, perhaps continue to be subleading even after resummation, because this Hubble to the fourth answer is very suggestive that's what the true result's going to be. Of course, strictly speaking, I haven't done the next leading log resummation. I've only done leading log. So if you want to say, what's the minimum thing I can claim to have done? Well, it's to say that if I didn't have the resummation in a phi to the fourth theory, I would have had to given up once times became of order the inverse square root of the coupling. That's when these different multi-loop contributions would be getting comparable, and I would have to give up on perturbation theory. But with this leading log resummation, I now can control this region. But of course, if I want to go to even later times, then I need to do higher order, etc. Okay. So as a quick summary, if someone, hopefully a friend of yours, wakes you up in the middle of the night a few months from now and says, what's something you learned at the cosmological correlators workshop? I hope this is a simple enough statement that it could be given in such a circumstance. And that's to say that, with this 35-year literature following on Starobinsky and trying to understand what exactly, was he right and why is he right? This can all be boiled down to, I say, the following very simple conceptual equation, which is to say, you take the power counting of de Sitter light scalar propagators, you put in the ingredient of causality, and you get out stochastic inflation. Or maybe, since names are sometimes easier to remember than concepts, it's power counting plus Weinberg equals Starobinsky. So of course, having reduced that to a conceptual one-liner, it's very tempting to think there's more that could be done with this framework. You know, one fun fact about the Fokker-Planck equation is it's a Markovian evolution. That's kind of interesting to me with a QCD background. That smells like the parton shower. You're trying to be an honest quantum physicist, doing full amplitudes and interference, and yet you're led to this notion of strict probability evolution. It's cute. Hopefully there's some technical meat one can hang on that. Probably more direct is to say, can we push further on this formalism as given? Can we say something about an escalating log, even though at that point this picture of strict classical trees convolved with each other via free quantum noise is going to break down? You're going to be able to have trees of retarded propagators that connect, say, multiple vertices or have loops. So those are no longer strictly interpretable as classical perturbation theory convolved with quantum noise. I think there's an interesting, it'll be interesting to tease that out. Of course, it would be nice if we had, along the lines of what Tim and Dan have started doing, if we could formulate this as a full effective field theory, as opposed to this more method of regions approach that we're taking for the moment. And then, this is a scalar on a fixed de Sitter background. It would be nice to extend this to include dynamical gravity, both for its own sake, because there are interesting infrared questions that infect gravitons in de Sitter backgrounds. And of course, once we allow for back reaction, then we really are doing a landscape and thus a warm up for real eternal inflation rigorous calculation. Oh. Okay, thank you.
Great, thank you very much, Matt. We have about 10 minutes, 10 minutes or so for questions. If anyone from the audience has one, please just speak up.
Can I ask one? If you did phi cube theory, would you see an instability? Like, I don't know, would these gammas be growing with time instead of decaying?
Yeah, I'm trying to think what. So I think one follow-up that I'd like to tackle, or it's out there, someone else could tackle, is the case of multi-minimum potentials, and how those are handled. I have a guess for that story is going to work out, but yeah, if I were to just put in a theory that just has no minimum, pure phi cubed, I mean, even the classical equations would be telling you that this theory is starting to roll away from you.
I think that's right, man. I think.
Yeah. But yeah, exactly where you would see it, I guess I'm not sure, but I can't imagine that theory is gonna, even at this level, is going to look safe. That you would somehow delude yourself into thinking that was a safe theory.
I think those capital gammas are ill-defined in some way.
Yeah. Well, yeah. In particular, just getting the zero. So in this purple solution, right? There's a zero mode,
Right.
and that assumes a kind of normalizability that I'm sure that phi cubed would run afoul of. So you would see there's no nice sort of attractive minimum that you're getting dragged to.
So we had a discussion of this on the first day. It's what I called outward drifting potentials.
Mm-hmm.
And that's what Spiros was using to find an interesting application of this sort of thing to, beyond low point correlators and non-Gaussianity. But, phi cubed is one thing, which has this deep instability, but there's also, more potentials that have regions with wiggles that go both ways. and calculating what you're calling the gamma ends is, you know, is of interest. And I'm not sure it's, even though it's a trivial calculation, once you have the Starobinsky story, you know, I'm not sure it's really been done or applied very much. So that still seems interesting.
Right. Yeah, I mean, what I'm guessing what happened in the multi-minimum case is that because you have this sort of Hubble budget for your energy, I would just, my ansatz is that sort of low barriers that can be fluctuated over by Hubble-sized fluctuations don't stand in the way. So as long as the barrier is only that high, given infinite time, you'll sample everything and you'll find the deepest minimum. But if you built in a barrier parametrically larger than Hubble, and you started the theory outside of it, I would think the theory then wouldn't find a deeper minimum. You would then pick up a dependence on your initial state and exactly what minimum you started. But I think it would be interesting and seemingly tractable to actually work that out.
Well, I think you have in mind some starting point where it's not distributed in its field space. It's, you know, some cluster, some origin, and then it's trying to find its way around.
Right.
But sorry, can I ask something else? I know I'm maybe asking too much, but it's interesting.
Costas has his hand up.
Oh, I'm
first,
sorry.
And then Eva, and then we'll move on to the next discussion.
Okay.
Okay, thank you. Can I ask, is there a similar story if you look at fermions, let's say massive fermions in the sitter?
Well, fermions don't have the same infrared divergence. There's, you know, if there's a sort of the massless limit for fermions, there's a sort of conformality that they don't, in a sense, they can't really distinguish that they're in de Sitter versus flat space. And the same is true for vectors. Actually, it's the interesting cases for picking up this deep infrared sensitivity are spin 0 and spin 2.
Thanks.
Eva.
Okay, what I want to ask is that, you know, there are quantum mechanical effects that can exist, you know, that are very quantum, like particle production, including repeated particle production in axion scenarios, for example. That involves multiple fields. I just sort of a sanity check, that wouldn't be, you know, being quantum, that wouldn't be in this kind of leading approximation, right? Just to make sure. I mean, one shouldn't confuse these equilibrium or approach to equilibrium results. We shouldn't confuse that with a complete systematic, you know, endpoint for the process in all situations. So, you know, what I have in mind are interactions among multiple fields that are not tuned to be small, but which, you know, I mean, again, this comes up in axion theories where there's repeated
Right.
Effects, and so the overall trend can be quite consistent with inflation, but then interactions are generically, you know, larger than the ones that give you.
So when you say large, do you mean non-perturbative?
Pardon? I just mean, you know, phi squared, chi squared, or really, you know, let's say, you know, a cosine of phi times, you know, times some other fields. Something that's, yeah, in that sense, non-perturbative because it's oscillatory. Anyway, this is getting too specific, but what I'm trying to say is that there are effects that can exist in inflationary physics that have been studied that are even testable that are quantum, and so go beyond this. Just as a sanity check.
I mean, I would certainly say that, you know, we were relying on the presence of an underlying perturbative theory that we could trust, at least for some duration, to set up.
Well, I mean, so what I have in mind is perfectly perturbatively calculable. At least it's calculable. You know, just the usual particle production effects.
Right.
I'm just stressing that those are quantum mechanical. They're not really difficult quantum effects. They're easy to calculate. Yeah, but I guess you're asking how do they fit into the.
Can I take a crack at it? So this word the word perturbative when you have large field transits, as you do in that kind of story that you're talking about, Eva, and I don't mean large as in Transplanckian, I just mean finite field, classical field evolution, that's already sort of doing, it may be easy to do because it's classical, but it's already doing a kind of non-perturbative thing by shifting the VEV or shifting the origin. Here, in some sense, everything is taking place in this, sort of starting from this departure point of, say, phi equals 0 or something. The closest thing already at the level of this discussion that Matt gave that is even reminiscent of what you're talking about with just one field is when you say have multiple minima, right? Like, which is what Matt was already talking about. Because you can see the subtlety in the story you're talking about is that, say, one of the fields can be like can set the mass for another field, right? You can right. And so already, if you just even freeze that field, it can or change that the dialing field. It can change, say, what is a positive mass term for some other field into a tachyonic mass term.
For example,
so all of the subtleties you're talking about, where there can be maxima and minima, even in the single field case, where definitely our work has not resolved it, come to bear in the story you're talking about. So it is very interesting, but it's just in terms of the thing that we actually did, it's scope of what we did, but it's in the ballpark of that.
Okay, thanks a lot. I just wanted to check that. By the way, just for everyone's benefit, a model where you do the Starobinsky stuff and V is linear and phi is analytically calculable. And that's actually a lot of fun. We played with it in some appendix with George, but it seems like it's something that could be used more if people find they want to calculate things that come out of this, more analytically.
Interesting.
Does it remain analytic? Can you couple it to gravity and play around with that too, or?
Let's see. I think we were. What I'm talking about is working with the Starobinsky formalism, and then but it's just you don't need numerics to work all this stuff out. That's all.
Gotcha.
Can I ask about a question that maybe has been? Oh, sorry. Was there another question?
Go ahead. This will be the last question before.
Okay. Sorry. Yeah. So maybe someone asked this already, but if we're interested in let's say we're talking about axions during inflation, or imagine sort of even imagine having it so that you have like a cosine potential, but that Hubble to the fourth is sort of big enough to let you sort of move around over the heights. Mm-hmm. Then in the kind of usual picture after inflation ends, we'd have different pockets where the axion is sort of stuck in different places and will oscillate, give you dark matter or whatever. But we're interested in correlations on not just averaging over one Hubble patch, but sort of the perturbations we'd get from the whatever the axion is here versus what it is far away. In other words, 2-point functions, higher point functions are interesting, but they are sort of dominated by the sort of intuitive picture of having the field move around. So can your formalism deal with that too?
I mean, once we can do I don't see any technical challenge to putting in a multi-minimum potential, but it's a different question. I'm not asking about expectation values of phi to the n, average over one Hubble volume. I'm now asking about sort of large. Yeah, well, I think you could combine. So Leonardo and Victor were able to get multi. Leonardo and Victor can get multi. Different. Can get x. Can get an arbitrary number of x's. I don't think there's any conceptual difficulty to if you have one x having two x's and so on. You pick up basically all these noise terms. The noise isn't it's no longer coincident noise. You can have the noise between this x1 and this x2. You get all these linking terms. I mean, Victor might know the equation better, or Leonardo, but so yeah, I don't think multi-minimum is a technical problem. I don't think multi-position is a technical problem. But they're not. I can't just hand you the equation at this moment.
I mean, it changes the gamma ones or the lambda ones that we talk about, right? That's the first thing to calculate, but otherwise.
Yeah.
Yeah. I mean, if you want, I can give some
So
detail.
in other words, if we give this sort of analogy with you know, normal infrared divergences, when you understand the IR, it means you can strip off as some universal thing the infrared divergence part multiplied by the hard process.
Right.
I'm asking whether you have that kind of whether this formalism is giving you that kind of division or not. I mean, what you'd like to see is that if you look at a multi-point function, you're doing some local Hubble scalar averaging in the neighborhood of both points. That gives you, there's some underlying hard process, and then you're addressing it. Is that how we come out of this formalism, or not? It doesn't have to, but I'm just saying that's what we're used to in other contexts.
Right. I mean, I'm tempted to say it could come out, but I think doing a calculation like the one you're describing would be the true test of it. And again, I don't see an obstruction to that.
I feel like that is our aspiration. That is sort of the mindset that we have, Nima. It's just that both of us are ploddingly slow, and so this is how far we got. So if we were to just guess our way, then I'd say, yeah, we could have the correlations in this kind of landscape for your axion and stuff like that, and there'd be kind of a universal infrared. We'd like to develop it to sort of see it like that, but starting from this diagrammatic point of view. But just in total honesty, no, we just haven't got to some of these non-trivial things. But I think what Matt is saying is correct. We do not see a showstopper from this diagrammatic view in doing what you're saying.
So let's end this part of the discussion here. We can continue it after the discussion of the other YouTube talks if there's time, but just to make sure we don't run too far over. Thank you again very much, Matt, for the nice talk and the fun discussion afterwards.